All right, so this is joint work with a bunch of people. And I've been working on that for more than 10 years, in fact. And we finally got the answer, I believe. So if you want to know more, it's in the proceedings of the TQC conference that took place a few months ago in Paris. So this talk is about key establishment. So let me first tell you what key establishment is. It's a game played between Alice and Bob, our favorite characters. And they are linked by a classical channel. Now, this channel is classical. It's public. Public means that there is no protection against eavesdropping. And in addition, it's authenticated, meaning that a tamperer cannot change the messages. Alice knows that it comes from Bob and vice versa. And how you implement authentication is not my business here in this talk. Now, the game in key establishment is that Alice and Bob, by public discussion, want to establish a secret key S, even though there is this nerd listening in. As I said, it's a public channel. There is no protection against eavesdropping, so this guy gets to hear everything they're saying. And what we want, of course, is that at the end of the day, Alice and Bob have this S in common, whereas the bad guy doesn't. And the brief history of key establishment, these are some of the key papers in the 1970s. The idea that it might be possible at all is due to John Ellis, who was working in the British Secret Services, not far from here. And he had the idea it might be possible, but had no clue how to do it. And Clifford Cox figured it out. So the first person who found a way to do that, as far as we know, is Clifford Cox. And in fact, he invented RSA essentially with a small variation. But independently, later on, other people thought about these ideas. Merkel and Diffie-Hellman in particular thought it was possible, and they both found a way to do that independently of each other and of Cox. RSA came later, and McGillis came later. And of course, in the game of key establishment in this conference, there's a couple of other people who did that, who worked on the problem of key establishment, but that's cheating. That's cheating because, as I said, we're talking about here a classical channel. So this talk, we restrict our attention to establishing a key we're only allowed to use a classical channel. Of course, if we use a quantum channel, then BB84 is much better than any of these things. But it's cheating here. All right, so I'm going to concentrate on Merkel. So of all these people, Merkel is the most interesting for what I want to tell you about. In particular because, well, he was first. Well, if you forget the spooks, Merkel in the open research was the first person to think about these ideas, the first person to find a solution. His solution is beautifully simple. If you're familiar with the Merkel puzzles published in CACM in '78, I think, that's not what I'm talking about. I'm talking about his original idea, which was much, much nicer than what he published. He could not publish his original idea because it's too simple. He had to make it more complicated to be able to publish. But in any case, Merkel in '74 thought of key establishment through insecure channels, authenticated. He found a way to do that, which unbelievably is all there in 6 lines. No point to read it, but if you're interested, go to this website. It's really very entertaining, where he explains his invention, how it was rejected by his professor, how he dropped out of the course, but how he kept working on the idea. In other words, but in any case, in 6 lines, Merkel explains how to do key establishment. It's remarkable. And then he felt that he was so simple that he had to also say that he's not joking. It was not good enough for passing the course. But anyways. So here's how it works. This is Merkel's scheme. I have to tell you about Merkel's scheme before I move on to my work. It's really very simple, completely classical for a few minutes. So here we have Alice and Bob, and we're going to assume the existence of what we call a black box function, which is a function from some domain which is known to an image. And the only it's black box because the only way you can gain knowledge about this function is by querying it. It's also known as the query complexity model. You can choose any x you want and push the button, you get f of x. And then you can choose some other x. So you see that with this condition, if you want to invert the function, let's say it's 1-to-1 for simplicity, it doesn't have to be, but for simplicity. If you want to invert the function, you're given some y, you want to find x so that f of x equals y. There's nothing else you can do than try at random. Because if you choose an x and find that f of x is not y, all you've learned is that this x is not the solution. So if there are n points in the domain of f, you will need n over 2 trials on the average. And there's no possible shortcut. So in this black box model, it's not realistic, but it's a model in which we can prove things. So that's why we like it. Good. So in this model, we're going to, in fact, we have n square points in the domain. And here's the protocol. Here's Merkel's protocol. You may have seen it before, but it's so beautiful, I can't resist telling you. This is the original 1974 protocol of Merkel, said in slightly different words, but essentially that's the way it was. So Alice chooses n points at random in the domain of the function, x1 to xn. She calls the function on these n points, gets n images, and sends all these images to Bob. And Bob's task is to invert any one of them. So to do that, Bob will choose a random point in the domain. Let's call it S. We'll call F an S and see is it one of these points. If it is, probably not. Then he will try again. Probably not. He will try again. At some point, he will succeed. So at some point, just by mere luck, Bob will find a pre-image of one of these points. And that's going to be the secret. But each try, you see, there are n squared points that Bob can try. And of these n squared points, n are good. These n are good. There are n good tries, possible tries out of n squared possibilities. So each try has a probability n over n squared of success, which is 1 over n. So there's a 1 over n chance of success each time, and therefore he will need to try on the average n times. So after n expected calls, Bob will be able to invert one of them, and that's going to be the secret. There. Of course, Alice needs to know which one it is. Well, that's quite obvious. Bob just tells her the index. And Alice has kept the table, so Alice knows what it is. And so now both Alice and Bob share this S. And they do that after about n queries each. Exactly n queries for Alice, and n expected queries for Bob. Now, how about an eavesdropper? The eavesdropper, this is what the eavesdropper sees. The eavesdropper has access to the same black box function, of course. The eavesdropper sees all these things from Alice to Bob, and one thing from Bob to Alice. And in fact, none of that is really useful, except, of course, except that knowing I, the eavesdropper knows f of xi. That should not have crossed the whole thing. but the only thing useful for the eavesdropper is he knows f of xi. He has to invert that particular point, and that will take the size of the domain divided by 2 on average, which is n squared over 2. So the eavesdropper needs n squared over 2 queries, whereas Alice and Bob need n queries. And that's a quadratic advantage. Now, quadratic advantage may sound not so good compared to RSA, or Diffie-Hellman, when we hope for an exponential advantage. But this is proven, at least in the black box model, there's a proof here. Whereas there's no proof, maybe factoring can be done, even on a classical computer can be done efficiently. We don't know that. That's why this is beautiful, because there's a proof. Good. And intuitively, Bob's advantage over the eavesdropper is that it's OK for Bob to invert any one of these points sent by Alice. Whereas once Bob has inverted one of them, the eavesdropper has to invert the same one. And that's much harder. That's where all the advantage of the legitimate parties come compared to the eavesdropper. OK, so that's Merkel's scheme. It's very nice. But now this is a quantum conference. So what happens if we replace this classical eavesdropper by our friend Makarov, or any quantum eavesdropper. Well, the quantum eavesdropper has a quantum computer, of course. Maybe Makarov doesn't. But against a quantum computer, this is pitiful because the eavesdropper knows f of xi and has to invert it. And of course, with Grover's algorithm takes a time which is to find the unstructured search. Grover's algorithm would be able to invert the function on essentially square root of the domain size number of queries. In fact, times pi over 4 to be more exact. So with pi over 4 times square root of the domain size n square, which is less than n, slightly less than n, the eavesdropper gets to find s as well. You can invert any given point. So it's really pretty bad because Bob needed an expected n. Bob needed an expected n number of calls. The eavesdropper does it with fewer. Pi over 4 is less than 1 times n. So it's complete break. And the question is, can it be repaired? All right. Now, the early solutions to this problem, how to repair Merkel's game, came in 2008. But then we required, this is joint work with Louis Salvail at the time, when Alice and Bob needed to have quantum computers as well. So it was quantum against quantum, which is fair game. But we all know that the bad guys are likely to have a quantum computer before the good guys. So it's much more fun to see if we can do a classical Alice and Bob against quantum eavesdropper. Is that possible at all? And the answer is yes. And this was, it took many years, but at QCrypt 2011, still many years ago, but at QCrypt 2011, with most of the co-authors of this talk, one fewer, we were able to give a Merkel-like classical scheme. Alice and Bob are purely classical, but at the end of the day, even we could prove that a quantum eavesdropper would need more time, more than linearly more time. Not quite n square, but more than n. And that was, in fact, this was the first, as far as I know, the first provably secure post-quantum crypto scheme, where by post-quantum crypto we mean a classical scheme that provably resists a quantum attack. Not an exponential gap, but at least provably requires the eavesdropper to work more than Alice and Bob. But why am I talking to you about this? It was 2011. What else is new? But nevertheless, let me tell you a few words about it then before we move on to the new stuff. This is how it worked. It starts the same way. It starts the same way as Merkel, exactly the same. Exactly the same. We have the same black box function. Sorry, and Alice sends the same information to Bob, f on n randomly chosen points of the domain. Same start. First change is that Bob finds not one but two pre-images. Well, it's twice as hard. No big deal. So Bob finds 2 pre-images. Takes about 2n queries, and the pair of pre-images will be the secret. Well, it doesn't seem like, why do we gain anything here? So now Bob has to tell Alice. Now Bob has to tell Alice how to find SS prime, how to find the 2 points that he's found. And of course, if Bob were to send the index of the 2 points, that would be no advantage over the original. So it has to be something else. And what we came up with back then in 2011, what we came up with is that Bob is we're going to need a second black box function, call it T. And what Bob will do, he will send to Alice a hash of his 2 points through T in this way. He will apply T to both points he found and do the bitwise XOR and call that W and send it to Alice. And so Alice will apply the function T to all the points that she chose at random, and Alice now needs to find 2 points here that XOR to W. This seems to take n squared time, but with a little thinking, you'll see that it can be done in n log n time, or even n time, with a little luck. So using the table, Alice finds the secret, and it requires about n queries on both sides. Maybe it's 2n queries, but order n queries for Alice and for Bob. And what we could prove in 2011 is that a quantum eavesdropper who has access to all this information will require more than order n times, in fact, n to the power 7/6. Now, this is ridiculous. Of course, practically speaking, you would not call that secure. But for a theoretician, it's really great because it shows that it's strictly more than n. So the eavesdropper has to work strictly more than Alice and Bob. And again, as far as I know, that was the first proof of anything at all in post-quantum cryptography. It's at least an existence proof that makes it worthwhile trying to find better. So that was 2011. And then, of course, it's tempting to allow Alice and Bob to be quantum. And if we do that, then we can modify the scheme a little bit. The first thing we do is we change n squared points in the domain to n cubed, because now Bob has quantum power that will allow him to use BBHT, if you know what that is, instead of Grover. So using BBHT, Bob can find pre-images, random pre-images in order n queries. And he will find not 2, but 3 of them, and then send the same thing, but with 3 instead of 2. And Alice, using quantum power, will be able to find the triplet that XORs the right thing. So with a quantum computer, Alice can find a triplet of points here that all of them together would XOR to the W sent by Bob. So it's still order n time and order n queries. So now we get Alice and Bob that have the same secret, S1, S2, S3. They've worked order n times and order n queries. But now it's much harder for the eavesdropper. It's harder for 2 reasons. One is that there are n cubed points in the domain instead of n square, which makes search harder. And the other reason is that there are 3 things instead of 2 that are mixed together. And then we could prove that the eavesdropper needs n to the power 7/4. Now, n to the power 7/4 is not quite yet n squared, but it's a lot less ridiculous than n to the power 7/6 that we had before. OK. This is all old stuff, and I have 5 minutes to tell you about new stuff. That's OK. I knew that. Also, last thing about the old stuff is that if we don't care about how much time Alice and Bob need, only about number of queries, if we really play in the world of query complexity, completely disconnected with reality and not taking care about time, then by using k, instead of 2 or 3, using k elements, and everything is the same, now we could prove that so it's order kn queries for Alice and Bob, but now we can prove that the eavesdropper needs n to the power 1 plus k over k plus 1 plus k over k plus 1. And when k goes to infinity, that goes to n squared. So we got back the n squared. However, this is totally unrealistic because the amount of time that is required by Bob to solve this riddle for Bob, given W, to find the k tuple that sums to W, we don't know how to do that efficiently, even with a quantum computer. So for query complexity, we get n squared back. If we care about time complexity, it's not so good. All right, the new stuff. So these were the first solutions, but there was a problem. At Crypto 2011, we only gave proofs that worked in the worst case, meaning that we could prove that the eavesdropper would require whatever number of queries I said in the worst case. But in cryptography, worst case is not relevant. What we need is a statement to the effect that with high probability, with high probability where the probability is also taken over the actual run of the protocol by Alice and Bob. So we look at the entire probability space where Alice and Bob run the protocol, get their key, and then the eavesdropper tries to find a key. And we want over all this probability space that with high probability, the eavesdropper is not able to get the key with less than n to the 7/6 or whatever queries. And so we worked very hard afterwards to fix that. We didn't work very hard because we thought we knew how to do it, so we submitted that to Journal of Cryptology. And it turned out that the referee found a little problem. Because for k equal 2, that's easy. For k equal 2, we can get from worst case to average case using the notion of self-reducibility. I don't have time to explain this, but it turns out that the underlying problem, which is called the k-sum problem, when k equals 2, the 2-sum problem is self-reducible, and the hidden, it's some technical thing that I won't have time to explain, but a hidden k-sum problem when k equals 2, which is at the core of the our lower bounds, that problem is self-reducible, so that when we have a proof, which we had back then in 2011, when we have a proof of hardness in the worst case, because of self-reducibility, we get a proof of hardness on the average just immediately. And we thought we were done, because we also had a proof of hardness in the worst case for any k, and we knew that for k equal 2 it's self-reducible, and we didn't think. But it turns out, so this makes it easy for k equal 2, and hence the n to the 7/6 for classical against quantum, and then the 5/3 for quantum against quantum, they work. They hold in a cryptographically significant manner. By the way, in case you paid any attention, you could be surprised by this n to the power 5/3 because I said 7/4. The reason is that this 7/4 here, which is bigger than 5/3, this 7/4 is for 3 queries, k equals 3. And with k equals 3, it's not self-reducible. So it's only with k equals 2 that we had to prove. In the case of k equals 2, when you take this formula, k equals 2, it's 1 over 2/3, 1 plus 2/3, which is 5/3. So that's why we get 5/3. So n to the 7/6 classical against quantum and n to the 5/3 quantum against quantum in a cryptographically significant setting of average case complexity, that was done. But that doesn't work for k bigger than 2. We still, to this day, we don't think that the hidden, I should have, of course, the hidden k-sum problem, we don't think it is self-reducible for k bigger than 2. So we need something else. And that's what this talk is about. In order to get the results for k bigger than 2, in the average case, in a cryptographically significant average case, we needed to develop new techniques, completely new techniques in quantum lower bound average case query complexity. If you're familiar at all with these query complexity lower bound results, it's almost only done in the worst case. You won't find very much average case query complexity work in the quantum world. Well, now you do. Now we've done it. That's what this work is all about. So, so we do get, in the end, we do get n to the 7/4, as claimed before. We do get n to the 7/4 lower bound on how much the eavesdropper needs to work even on the average. So this is cryptographically significant. It's not n squared, but it's getting there. And if you don't care about time, but only about queries, we get up to n squared. So the previously claimed results are correct, but we needed completely new proofs to make them work. Okay, so in the 1 or 2 minutes remaining, I'll give you an idea how these proofs are done. I knew I would not. There's no point giving technical details in a talk like this, but I just want to show you that they exist. The hidden k-sum problem is the following. It's still worth taking 1 minute telling you what this problem is. This is function f. This is the function f. I remind you that Alice chooses n points at random. There are n square points in the domain. And Alice chooses n points in this domain and computes f on these n points, sends it to Bob, n to the eavesdropper. These are the red values. So Bob and the eavesdropper get to see these red values. Now Bob has to invert k of them at random and send the XOR of the t values to Alice. Now, each one of them, this is a corresponding t value. It's not that t of 17 is 24. It's that 17 is f of something, and t of the same something is 24. So the eavesdropper sees these red values, and what the eavesdropper really has to do is to solve the k-sum problem, meaning to find k of these gray points that sum up to the w that Bob told to Alice. But the eavesdropper does not have these values. He has these values. So the eavesdropper sort of needs to compose two problems. One is to find t of x given f of x, And the other is if he had all the t values, to find k of them that sum up to w. And what we could prove is that, and this is not an obvious thing at all, but we could prove that the complexity of the joint combined problem, or the composed problem, is the product of the complexity of the two underlying problems. And so, right, so going from here to here, we call it p-search. Going from here to here, we call it k-sum. P-search takes n to the 1/2. K-sum takes n to the k over k plus 1. And when you multiply them, we get this. This is for classical against quantum. If it were quantum against quantum, this would become n, and we'd have 1 plus k over k plus 1. But for classical against quantum, we have multiplied this by this, we get that. But that the complexity of the combined problem for the eavesdropper is a product of these two is not at all obvious. I'll show you the proof here. That's the proof. Okay. But all that we had already many years ago in the worst case. Now we have to do it in the average case. To get in the average case, we need to use the adversary method. And I was very, very careful to spend enough time of my allotted time before I get here. I don't have to explain this to you. So that's how it works. So we use the adversary method like this, like everybody would do. And so we need these matrices. And in particular, the really new thing here is that we use variations on the quantum adversary found by our co-author, which is used to distinguish between two distributions. So we have two different distributions, and we can distinguish between sampling from one and sampling from the other. And for that, we need these new lower bound techniques. We also need a new composition theorem that applies in the worst case, it applies in the average case. And when all of this is done, at the end of the day, we get a proof. So open problems, again, it's all in the glory details in the proceedings of TQC. So if you really care about it, go there. It will soon be on the archive as well. So to sum up, we have open questions. I'd say the most important open question, I would say, is the last one, which is that for k equals 3 in the quantum, if Aleksandrs Belovs were quantum, then it can solve the three-sum problem in linear time. And therefore, the protocol is efficient time-wise in addition to query complexity. So that's for quantum against quantum. For classical against quantum, we don't know how to do that efficiently with k bigger than 2. So k equal 2 is the best we can do in terms of efficiency for classical Aleksandrs Belovs. K equals 3 for quantum Aleksandrs Belovs. So if we care about time as we should, and not only about query complexity, we're stuck there. And we get this n to 7/6 for classical against quantum, and n to whatever it was, 7/4 for quantum against quantum. And the main open question here is try to do better, try to find maybe a different way that would be efficient in terms of time and query complexity, and probably hard for the eavesdropper in terms of query complexity. In the classical world, we know that in this kind of model, in the classical world, no matter what scheme Aleksandrs Belovs invent, the eavesdropper can always break it. If Aleksandrs Belovs you use order n queries, then the eavesdropper can always break it with n² queries. That was proven some years ago in the classical case. We don't know about the quantum case. So it's not impossible in quantum case we can do better. It's not unlikely, but not impossible. So the main open problem is this. Try to find the best possible, or at least better than we have, protocol in this model. In this model, we use this model because we can prove things in this model, so that the eavesdropper would have to work as much as possible, provably so, compared to Aleksandrs Belovs in the cryptographically significant setting of average case complexity. And I'll stop here. Thank you.